So infiltration is the process by which water enters the ground. So we talked about how soil water can move in unsaturated and saturated conditions. This is when you have precipitation and the water's coming down, percolating into the ground, infiltrating. The curve that I show you here is a typical infiltration curve. And what you'll see is initially the infiltration rate is very quick. So when soil has not had any water in it, the water will go in very rapidly because the intake of water is dominated by capillarity. So all the small pores in the soil will rapidly absorb any water that's coming in. And then over time, as the water's infiltrating in, it'll start to fill those small pores, and then the large pores start to fill. And then when those large pores are draining, as the water's moving its way down the soil, that is dominated by gravity. And so at this particular point, we call that the stabilized rate. And so what you'll see is a very rapid infiltration, and then it tends to flatten out. And so when we start seeing that stabilized rate, that's the rate that we normally want to use to represent our soil condition. Infiltration can be measured a variety of ways. The simplest way is with a ring infiltrometer. In this particular case, this is a single ring infiltrometer. You just put essentially this cylinder down into the ground, and you fill it up with a known amount of water, and you time how long it takes that water to go into the soil. And then you repeat that over time. And so that gives you a good indication of at least the infiltration rate of your surface material. Now the problem with the single ring is not only does water go down, but when the soil is dry, water also transfers out laterally. So if you're concerned about that, then people oftentimes use a double ring. So you have this single, and then you surround it by another ring. So imagine this setup with another ring around it. And you keep both of them at the same water level. But you only measure the infiltration rate on the inner ring. And so this way you have water infiltrating down all around here, but you're only going to be measuring the downward rate in the single inner cylinder. We also get infiltration data from rainfall simulation experiments, where we will use a little bit more sophisticated system than a ring infiltrometer. Typically you set off an area, you cordon it off, and then you pump water in at a known rate to simulate rainfall conditions. And then you measure the output of the water, and then also we'll use time domain reflectometry, soil moisture sensors, or tensiometers to get at the matrix potential or the soil moisture content. So this is really useful to get pretty accurate information on the infiltration capacity of your soil. And some of these can be rather large. There's been rainfall simulators that have been built that have measured water infiltration over very large areas, quarter acre, half acre plots. So we're not going to measure infiltration in this class. We're just going to talk about it a little bit. And so this is a horrible slide. I realize that. It's got a lot of information here, but I really just want to talk about some of the key factors that affect the infiltration rate. And the first one and main one is your soil texture and structure, because this controls the porosity in the soil. And the porosity is where the water is going to go. And the biggest influence humans have on texture and structure typically comes from compacting soil. So when you compact soil by, say, driving heavy equipment over the top of it or purposely compacting it for a road, you change the structure of the soil. And with a more platy, compacted structure, you have less porosity. And so you reduce the infiltration rate. And so it's this compaction and change in structure where we oftentimes get overland flow from rain precipitation. because the water can't infiltrate into the soil rapid enough, and then it starts running over the surface of the land, which speeds up its delivery to streams, but also creates greater soil erosion. How hydrophobic or hydrophilic your soil particles are will affect infiltration. The previous water content, the capillarity that dominates the first part of infiltration are the small pores filling. And so that tends to be very rapid infiltration. However, if you already have those pores filled, then you may go straight to a stabilized rate. So you may not infiltrate as much water when you have, say, some antecedent water conditions in the soil. Another effect that human beings can have on infiltration is the quality of the water that's going to infiltrate into the soil. In natural conditions, say after a fire, oftentimes there's a lot of surface erosion, and so small soil particles are moving across the surface of the land. That silt and clay can fall into the small pore spaces on the top of the soil and basically plug up the soil. That'll really reduce its infiltration capacity. Oftentimes we want to infiltrate water on purpose. Say we have runoff from a parking lot or something like that, and we don't want to change the hydrology of the local stream, so we may put it into a catch basin to infiltrate it. And if there's a lot of sediments and other turbid sort of parts in the water, that can do the same thing. It can plug up the pore spaces, affecting the infiltration rate. Biological activity generally is going to improve your infiltration rate. Things like squirrel burrows, anthills, wormholes, all of these create porosity in the soil. So good biological activity, healthy organisms living in your soil promote infiltration. Coming down to the bottom, a couple other key ones. Temperature. If you have frozen ice in your soil, frozen ground, you're not going to get any infiltration. And in fact, in some cases, this is something you can use to your advantage when it comes to, say, developing land or doing activities on soil. If you want to put some heavy equipment across ground and you don't want to compact the soil, doing it when the soil's frozen is an ideal time to do it, because the ice and so forth will help hold the soil structure. And then finally, rainfall intensity. Rain does not fall evenly at the same rate at all times. And so when you have more rainfall coming in, you're going to have more infiltration. Less rain coming in, less infiltration. And so depending on the varying intensity of the rainfall, you might overwhelm the soil with a high intensity rainfall, but then maybe have a little bit of break where the intensity is lower and the infiltration gets to catch up. So that varying rate of infiltration capacity of rainfall intensity can oftentimes ensure that most of the water from the rain event will infiltrate. So here are some common infiltration rates for soils. We have the texture over here, and then you can see rates in millimeters per hour. In San Luis Obispo, a very extreme, unusual rainfall intensity would be 1 inch per hour. And so that relates to 25.4 millimeters per hour. And so if you look at most of these soils, particularly the sandy loams, clay loams, and even the higher end of the range of the clays, almost all of them will infiltrate water at a rate higher than this very intense rainfall rate. So the point is that the infiltration capacity and rate of undisturbed soils is typically high enough that it can absorb most of the rainfall intensities that happen around the world. In fact, it is very rare to see overland flow on natural soils. Yeah, you occasionally see ponds and lakes. You'll see puddles, but oftentimes those are very much anomalies. And they may be associated with, say, some compaction or something that's happened from some development or some other activity. Generally speaking, undisturbed soils will infiltrate the rainfall intensities. So water generally moves in the subsurface. Seldom does it move over the surface of the land. And this is very true when you start talking about forest soils. Here's some infiltration rates from various mountainous forest environments in the Western Cascades. And notice that the units now are in centimeters per hour. So in the Western Cascades, they've measured upwards of 600 down to maybe 76 centimeters per hour. 1 inch per hour is 2.5 centimeters. So very high infiltration rates can handle a lot of water. Coast range measured at around 360 centimeters per hour. And when you start getting into the compacted surfaces, though, you can see that infiltration rates can be really small. And so in our compacted surfaces, like our roads and so forth, we oftentimes expect overland flow because rainfall will come down, it can infiltrate the soil, and so then it runs across the surface. However, there are definitely instances on roads where there is still infiltration capacity. So it's something to take in mind when you start thinking about how roads can change hydrology and how much they infiltrate. Not always do they completely run all of the surface water that are delivered to them. All right, so your water has infiltrated the soil. A certain amount of it will be stored in that soil. It'll be used by plants. A certain amount will evaporate. And the remaining amount will seep down to deeper layers and create groundwater. And so let's revisit our global water cycle. We looked at this back in week 1, and we looked at where the water was in this planet. And the majority was in salt water. But when it came to fresh water, the second greatest place for fresh water is in the ground and soil. And so it is a water source that in modern times we're widely using. And it's a water source that's been used actually historically, but we're particularly accelerating our use of it. So I think it's important for you to just get a few basics about water in the ground and what that means in some of the terminology. And then we'll show you how you can calculate how water moves in the ground. So what is groundwater? When I define groundwater, I define it as the rock and soil media that has its pore space fully filled with water, completely saturated conditions. This is groundwater. Then when you get up to unsaturated conditions, where you only have pores partially filled with water, then I call that soil water. Now you'll find some people that will say even the unsaturated water they'll call groundwater because it is water in the ground. And that's okay. But generally speaking, when I think of groundwater, I think of saturated conditions in amongst the soil and the geologic media. And a couple common terms we use with groundwater are the aquifer. That's the water-bearing soil or rock. So this is the porosity where the water resides. And not only is it the media, but usually when we talk about the aquifer, we mean the media and the water that's residing in that media. And then important to how much water is easily usable from groundwater, we use the term specific yield. And so if the water was just allowed to drain by gravity, what would be the amount of water that you get out? And actually specific yield is, well, in my definition here on this slide, I call it a ratio, but it can be a ratio or volume. It's represented both ways. And that's that water that would drain out by gravity. And so this is the volume or the ratio of water that drains to total volume that is usable, at least easily usable. And so why do we have a term like specific yield? Well, it's because that groundwater is not just an open body of water like a lake in the subsurface. When we talk about groundwater, the majority of the time what we're talking about is all the little cracks and pores in the subsurface being filled with water. So usually the majority of the media is the rock and the mineral, and the minority are the openings where the water resides. So cracks and bedding planes and so forth are the places where the groundwater is residing. And so if you drain this out, because it's all caught up in these pore spaces, we have capillary forces, we have adhesion of water to these different particles. So not all of it is easily going to come out. And indeed, if you look at some of the geologic media where you would find groundwater and look at the porosity associated with that media, you can see you can go from anywhere from 50% porosity down to maybe only 10% of the rock actually has space that can hold groundwater. So knowing the porosity and your specific yield is very important to managing your groundwater. So we define specific yield as that water that would freely drain, if you could freely drain by gravity, that would come out of your aquifer, out of your groundwater basin. The opposite of that is the specific retention. And it is the amount of water that would be retained. And so when we start talking about hydrogeology and thinking about managing water resources and groundwater, you really need to think of both of these factors. And so this graph down here I put in your notes, and it shows different soil geologic media where you might have groundwater in amongst the pore spaces. And you can see in some of it, like for example, very fine materials like clay silt type deposits, your specific retention, let's say it's 50% porosity, might be as high as 45%. In other words, you would only get a specific yield of, say, 5% of the total. So obviously, the types of aquifers are going to be most beneficial for things like storing groundwater, managing groundwater, are going to be those particles like sand, gravels, and so forth, where you can get a very high specific yield and a low specific retention. So this map is put out by the United States Geological Survey. It's just a very gross, large-scale map of the various groundwater aquifers that have been mapped in this country. Moving into California, you can see the San Joaquin Valley here. Huge aquifer in California. When we get down here to, say, the San Luis Obispo area, you can see in around San Luis Obispo, the Los Osos Valley and so forth, there is an aquifer there that needs to be managed. And of course, up in Northern County, when you get above the Coast Range, Paso Robles and some of those groundwater areas, the Salinas Valley up here, all important aquifers. So groundwater is ubiquitous. It's most everywhere. They don't really show a groundwater basin in the Sierra Nevada, but the reality is there is groundwater, and that groundwater is working its way, and then it gets caught up into the San Joaquin Valley. So water moves in the subsurface, and very important part of our water resources. So what are the different types of aquifers, and why is it important to understand that? Well, first off, the different types. The type that we probably most think about are unconfined aquifers. So you have no overlying layer that is creating any sort of, that is not holding the water in. an aquitard. If there's an aquitard present there, then it would not be unconfined. So unconfined aquifers, pretty much if you have infiltration that comes into the soil, it will reach the groundwater. And the water table, the surface of the groundwater, is essentially the top of the aquifer. Conversely, confined aquifers are aquifers where water has, say, moved into the subsurface in some other location, and it moves. In this particular cartoon here, it's showing you water moving downhill. It finds itself moving underneath a confining layer. So that may be a bedding plane of very dense geologic material. It could be maybe some clay and silt lenses and so forth that are highly impermeable. Could be a mix of clay and organic materials that are hydrophobic, that are creating a confining layer. And so the difference with an aquifer in a confined situation compared to unconfined is because it's confined, this water is under pressure. So when you put your well in, oftentimes the water will come out at a very fast rate because you have the pressure of all this water above it weighing down on it. And in fact, the term artesian spring comes from the fact that it is water, groundwater, that is coming out of the ground from a situation where the water's been under pressure. So in other words, it comes out very rapidly. Putting in a well that spews out water would be an artesian well. And finally, a more localized condition that can happen are perched aquifers. So typically a perched aquifer is just a localized area where you maybe have a small confining layer where water will sit on top. So it infiltrates down, it sits on that sort of perched clay lens or rock bedding material. And usually all around it, though, there's an unconfined aquifer around it. So it's localized. But it's a typical condition that you find on hill slopes. And so oftentimes perched aquifers are where you get some of your surface water and spring situations happening. But it also happens out in large basins as well. So it's something that you have to be aware of. If, say, you're doing a groundwater investigation and you're trying to find, say, the depth of groundwater around your groundwater basin, you have to take several measurements, because if you just take one and you happen to hit this perched water table, you may actually think that the water level is higher than it actually is. So perched aquifers. All right, so water moving in the subsurface is going to have different reactions compared to water running over the surface of the land. The main reason is because water is not moving in sort of an open channel. It's now having to work its way through all the little pore spaces. And so it has pressure involved there and also gravity, but there's a lot of resistance from the media that's going to slow the water movement down. And so we're just going to look at one equation that can help us predict that. That is Darcy's equation, also known as Darcy's law. And it's probably the most important equation that you can use when you're talking about groundwater movement. We're going to use it in just a very simple sense, and we'll try a simple example. But I do want you to understand what Darcy's law is and how you calculate with it. So in this particular diagram, I'm showing you the Darcy's equation to predict velocity. They're using little q here because they're really truly talking about flux. But in this case, we can just think of it as velocity. So ultimately, our units are going to be length per time. Now you can also predict discharge, so volume per time. And the only difference is you predict for the velocity, which is length per time, and you multiply it times the cross-sectional area that the water is moving through. So here's a classic textbook diagram of measuring hydraulic conductivity in water movement in, say, in this particular case, the geologic material is sand. And so this would be the cross-sectional area here that the water would move through. Okay, so let's talk about Darcy's law. Q equals minus K times D sub H, D sub L, sorry about that, times A. So first off, the K factor. This is the hydraulic connectivity. And the hydraulic connectivity is what represents one, properties of your media. So this is the rock or the soil. And what is meant by the properties is essentially the resistance to water movement. You could think of it as friction, but really the term we use is the tortuosity. So here we have an aquifer composed of, say, lots of little gravel particles. All right, so if you had water moving in an open channel, it would just take the path of the channel. But in the case of groundwater, the water has to take a very tortuous path. And as it's going through here, it's being subjected to things like adhesion and the roughness of the material itself. So we need some term that will actually help us account for that. And so the hydraulic connectivity essentially is the value that tells us in length for time the rate of movement of the water. Okay, the second one is the properties of the fluid. So our hydraulic connectivity takes into account essentially the viscosity of the fluid. And viscosity is essentially just, it's essentially a measurement of how well the molecules will flow amongst each other. And so if you have very high viscosity, you're going to have slow movement. A highly viscous material would be things like, say, honey. Very slow movement. The molecules itself in amongst the honey are not going to travel across each other very quickly. And, low viscosity would be things like water, or even lower, how about things like petroleum products like gasoline. Now, usually what we're using Darcy's law is to predict water movement. However, let's say if you have a contaminated material that's spilled into the groundwater, understanding the viscosity of that material will help you understand the movement of it. And a lower viscosity material will move more rapidly in the subsurface than a higher viscosity material. In the case of water, though, the biggest influence is temperature. And so when water's at a low temperature, it's going to have a higher viscosity. When it has a high temperature, it's going to be a lower viscosity, and so it would move faster. So your hydraulic connectivity essentially is this magic number that you use to control your calculation based on the properties of the resistance of the media and the viscosity, or the properties of the fluid that's moving through the media. Okay, so we also have gradients and head. So H is essentially the change in elevation of the groundwater surface. Excuse me, H is the elevation of the groundwater surface. D sub H would then be the change. And we show it as a differential equation. In our particular case, we're going to look at it as a linear type of relationship. And D sub L is the change in length. So this is the length of say, your aquifer, change of length of the flow media. Okay. So let's go ahead and set up a situation here. You've got, say, the ground. I'll put my tree on top of it, and let's say I have an aquifer here. Okay. I can measure the elevation here, and I can measure it, say, up here. All right, I don't want to say high, I want to say H sub 1. So D sub H would be, in a linear fashion, the difference between H2 and H1. It's simply the change in elevation here. Now notice I put the downslope elevation first. That's because D sub H is typically a negative value. You are using energy. Work has happened in order for water to move by gravity, by pressure, from H1 to H2. So the way we account for that is we make that value negative, and you can make it negative simply by putting your lower elevation, subtracting your higher elevation from it. Now the reason we show it as a differential equation is because this is a solution that's really linear, so really I should write it this way. If we're talking about D sub H, really what we're talking about is integrating across this surface over the length that we're talking about here. And so D sub L, or DL, is just this length of the aquifer. And so if we were using calculus to go ahead and tell us the variations in this surface, that's why they represented it as a differential equation. However, we're only going to solve it in this class as a linear problem. All right, well, let's look at, first off, hydraulic conductivity. So it is a property of the geologic media that provides resistance, and also property of the fluids. And so there's plenty of published values on this that you can use to help you predict your groundwater movement. You can see here's some various factors in meters per second for different geologic material. So highly variable, but there are a lot of published values that will help give you a good indication of your hydraulic conductivity. You can also take samples of your media and send it to a lab to get measurements of the hydraulic conductivity. So let's look at a simple calculation with Darcy. So here's our situation. We have a sloping hill slope. We have groundwater here. We can measure the elevation of the water table. You're given your hydraulic conductivity and some other dimensions associated with the hill slope. And what we want to find is the subsurface flow out of this hill slope, and we're going to have time involved. So we want to find it in 1 day. And so flow in this particular case, let's go ahead and do discharge, or cubic volume, cubic length per time, volume per time. Okay, let's see if I have enough room here. So I'll write this out as Q equals minus K dH dL times our cross-sectional area. So now it's just plug and chug. We know our hydraulic conductivity, so it's a negative value. Just like the change in head, the change in elevation, the DH, hydraulic conductivity is negative as well. That's because it takes energy out of the water as it moves. It's a resistance, so we represent it as a negative number. Okay, that's in meters per second. All right, so our change in elevation, d sub h, is h2 minus h1. h2 is 10 meters. h1 is 70 meters. And it says the flow path length is 100 meters. So there's our dl. All right, now we need our cross-sectional area. So we have this situation. They're telling us that the flow length is 100 meters and the width is 100 meters. And our soil, and this is not to scale, is 2 meters deep. The water table depth is 1 meter. So what they're saying is you go down 1 meter and you will have your water table. So in this particular case, because we have a 2 meter soil and the water table is down 1 meter, our water depth of our aquifer is 1 meter. And the cross-sectional area is simply that area that the water is going to move. So A is going to equal to our aquifer depth, 1 meter, times its width. So 100 square meters. And then you plug and chug, and you'll end up with meters per second if you multiply and do all these different calculations. So basically what we have to do is just convert 86,400 seconds today to get ourselves a flow per day. All right, I'll let you do that calculation yourself. So this lecture we talked about how water infiltrates soil, how it's more rapid at the start due to capillary processes. And then as the soil fills up with water, the infiltration rate gets dominated by gravity. That's usually the rate that we want to be concerned about. Generally speaking, infiltration rates, infiltration capacities of undisturbed soils are higher than rainfall intensities. So it's very seldom that you get overland flow of water in undisturbed soils. The water infiltrates in the soil. Groundwater is an important water resource. It's a big part of fresh water on this planet. And so we talked a little bit about how you can get the yield, how you calculate the yield from the groundwater. We talked about a couple of different aquifer types and how that influences what you're looking at with the water, confined, unconfined, compared to perched. And then finally, Darcy's law with a simple example of how we calculated water discharge through the subsurface. Thanks for your attention.